There are a few concepts in organic chemistry that you have to know cold. You have to know without thinking about them, that you have to take for granted if you want a chance at being a true OChem ninja. I call them the OChem Non-Negotiables. Today's topic, finding hidden hydrogens. Finding hidden hydrogens in a line angle structure is maybe the most core non-negotiable skill of all. If you'd like to look at some of my other non-negotiable skills, I have the playlist that I'll link to down below. When we draw line angle structures, the hydrogen atoms are implied, but they're still there, and you still need to be able to see them even if they're not completely drawn in. Being able to look at a molecule, go down the line, and tell me how many hydrogens are on each molecule is a non-negotiable skill. You need to be able to do it without even really thinking about it. Most of the time, it's fairly straightforward. Carbon makes 4 bonds, so if there's a carbon with 1 explicitly drawn bond, there must be 3 other implied hydrogens attached to that carbon. If there's an alkene, then there's 3 explicitly drawn bonds, and there's only 1 implied hydrogen. And so on down the line. This skill is important for something like drawing resonance contributors, one of the first truly challenging concepts that students come across in organic chemistry. When I teach organic chemistry over and over again, I will see students try and draw a resonance contributor of this molecule, making a double bond on the left. And for students who struggle with counting hidden hydrogens, this looks like it should work just fine on paper. But by being attentive to hidden hydrogens, we will see that there are 3 hidden hydrogens on this carbon on the left. We don't have any arrows breaking any of those bonds, so there must still be 3 hidden hydrogens on this carbon on the left, and that makes 5 bonds to carbon. You can't have 5 bonds to carbon. This is an invalid resonance contributor, and if we hadn't counted out the hidden hydrogens, we may not have seen that right away. Similarly, in resonance land, I'll see students try and take a lone pair of electrons to drop down to form a new carbonyl. Again, on paper, this seems like it should work just fine. But when I see a student try and do this, it tells me that they're not really counting hidden hydrogens. This central carbon atom has 3 explicit bonds, so there must be 1 implied hydrogen attached to that carbon. Again, I don't have any arrows showing that hydrogen-carbon bond breaking, so it must still be here in this product, and that again gives us 5 bonds to carbon. You still can't have 5 bonds to carbon. This is another invalid resonance contributor. Both of these could have been avoided by plotting out the hidden hydrogens. Do we need to show every hidden hydrogen on every carbon atom in every structure? I mean, when you're just starting out, if you're having trouble, yeah, maybe you should. As you work your way up to higher and higher ninja levels, maybe you don't have to draw out every hidden hydrogen every time. But a good rule of thumb that I would recommend is to always draw out the hidden hydrogens near the reactive center. At least by slowing down long enough to draw in the hidden hydrogens near the reactive centers, you have a better chance at seeing some of these mistakes before they happen. Over time, this will start to become second nature, and maybe you won't have to draw them in each time. Another situation where it's helpful to draw in the hidden hydrogens is where we have a carbocation that could be prone to rearrangement. Carbocations can do one of 3 things. They can do elimination, like E1 reactions. They can do coordination, like SN1 reactions. Or they can rearrange. Every time we draw a carbocation, we must look for rearrangement. Not every carbocation will rearrange, but we do have to check. If you'd like a refresher on carbocation rearrangement, I have a playlist down below that I'll link to. If this molecule were a reactive intermediate in a mechanism, you might get so caught up in the mechanism that you forget to check for rearrangement. But by slowing down and drawing in the hydrogens around the reactive sites, we can see that there is 1 hydrogen on the left that could be prone to rearrangement. We wouldn't rearrange to the right, we wouldn't form a primary carbocation. But by sketching in the hidden hydrogens around the reactive center, we can see that there is a hydrogen on the left side that could rearrange, and that would form a tertiary carbocation. Had we not drawn in the hidden hydrogens, we might have missed this rearrangement. On the flip side, it's also important to be able to look at carbons and tell which carbons do not have any hidden hydrogens. I can't tell you how many times I've seen students draw in a hydrogen here and try and do a carbocation rearrangement with this hydrogen. This benzene carbon already had 4 explicitly drawn bonds. There are 0 implied hydrogens on this carbon. Even though it looks like it's more substituted than the original secondary carbocation, we cannot do the rearrangement because there's no hydrogen to rearrange. In acid-base land, if you're presented with a molecule and a base and asked to deprotonate this molecule, then without the hidden hydrogens drawn in, you might be tempted to deprotonate this CH3 group because it's the only hydrogens you can see. These hydrogens, however, are alkane-type hydrogens with a pKa around 50 or so, and they will not be deprotonated by sodium methoxide. Instead, by drawing in the hidden hydrogens, we can see there are 3 hydrogens on the left and 2 hydrogens on the carbon in the middle. From here, you would need to notice that these are alpha-type protons on the carbon next to a carbonyl, and they have a pKa of around 20 or so. This isn't a video about pKa's or acid-base chemistry. I do have a playlist that I'll link to down below, though. But I would want us to see that these 2 hydrogens in the middle are flanked by 2 carbonyls, 2 electron withdrawing groups, making these hydrogens more acidic than we would otherwise expect. Our base, then, will attack these interior hydrogens to form the conjugate base. In practice, having these 2 hydrogens flanked by 2 carbonyls severely drives down the pKa. These hydrogens have a pKa of around 10 or so. This last example comes to us from substitution and elimination land. If you haven't gotten to any of these concepts yet, don't worry about it. You will. You'll see it when you get there. But in elimination land, potassium T-butoxide is a big bulky base that will do an E2 elimination. It can be important to draw in the hidden hydrogens around the reactive center when doing something like an elimination reaction. Zaitsev's rule says we would take the hydrogen from the most substituted beta carbon, but potassium T-butoxide is a big bulky base, and so it's too sterically bulky to remove this hydrogen. Instead, potassium T-butoxide tends to give a non-Zaitsev base where we take the hydrogen from the least substituted beta carbon. I suspect most students can find the two hydrogens that are hidden on the carbon to the left. But if you're not careful, you may miss the 3 hydrogens attached to this methyl group up top. These hydrogens are the least sterically hindered hydrogens, and these hydrogens are the ones that will be attacked by potassium T-butoxide in this E2 elimination reaction. The big bulky base non-Zaitsev elimination will form the double bond with this carbon at the top. Failing to draw in the hidden hydrogens may trip up even a higher level ninja if they're not careful. Go ahead, give yourself a little pop quiz. Walk through this structure, see if you can tell me how many hydrogens are hidden on each of these carbons. If you have trouble walking through the molecule and telling me 3, 1, 3, 0, 0, 2, and 3, then let's slow down a little bit. Let's go practice some hidden hydrogens, make sure we really understand this skill before we get too much further in organic chemistry. Finding hidden hydrogens is one of the key OChem non-negotiable skills. Let's make sure we have it down now before it causes problems later on. If you can truly internalize this skill, then you're ready to embark on the next phase of your ninja journey.
I'm glad you're here with us for this training today. Check out these other videos in my playlists to see if there's anything else that can help you level up your ninja levels even further. As always, don't forget to like and subscribe.